In this video, we're going to continue our idea of normal force, and this time we're going to talk about when you're in an elevator and what happens when your normal force changes. For example, I'm sure we've all ridden elevators and we've gone up in an elevator and you notice that you feel different at the beginning of the ride compared to the end of the ride. And what we want to do is kind of show what's actually happening there. So these are really just simply FNet or net force kind of problems where we're going to have to look at the forces that are affecting our person down here. Now I'm going to kind of draw this on the floor of the elevator because that's kind of where our normal force is happening. And there's two forces. There's our typical weight that's pulling that person down, and then there would be the normal force, or in this case we'll call it the force of the elevator, which is going to push that person upward. Now we're going to look at 4 different scenarios, and we're going to start with going up. We're starting upward with an initial velocity equal to 0 meters per second, which means we're starting from rest and moving in the upward direction. And the acceleration then is going to be a positive 2, and we're going to basically say that everything moving upward in this case is positive. So that's our direction for positive versus negative. So I guess to start, we just want to simply define our equation. So the net force acting on this person is always equal to mass times acceleration. But in this case, by saying up, we have the force of the elevator, positive, minus the weight of this person. Now the weight is mass times gravity. And we can see our person has a mass of 100 grams, and that doesn't change, or 100 kilograms. Doesn't change. So you go 100 times 9.8 meters per second squared. That's going to give us a weight of 980 newtons. So when we go back up into here, we're going to have 100 times our acceleration, which is going to be 2 meters per second squared, is equal to the elevator force, or our normal force, minus 980 newtons. So I end up with, and I'm kind of scrunching for room, so I'm going to kind of use little arrows here. We're going this way. 200 newtons is equal to the elevator force minus 980 newtons. Then, when you combine like terms, our elevator force, which is our normal force, is going to equal 1,180 newtons, and that's in the upward direction. So what it shows, and it should make sense, is that we're going to now take this person from rest, accelerate them upward. The elevator has to at least support the person's weight and add 200 extra newtons of accelerating force to make them go up. So that's why sometimes we'll feel heavier when that first starts to go up, because the force of the floor against us is greater than our actual weight. Then we're going to go to the next part. Now we're on our way up, but now we're going to stop. So we have gotten to a speed of 2 meters per second, and now we're going to stop. Now, the nice thing is this never changes. It's still the weight going down and the force of the elevator floor pushing us up for our force diagram. So there's really no difference there than what we had. Oops. Sorry, let me redraw that. Weight and force of the elevator. So our equation stays the same. The net force equation, mass times acceleration, is equal to, again, still the force of the elevator, positive, minus the weight, which we defined as negative. So again, I'm going to put my numbers in. I'm going to have 100 kilograms times negative 2 meters per second squared here. Because now we're stopping. So we have to slow us down. That's going to equal the force of the elevator minus the weight, which is still 980 newtons. Now, I'm going to end up with negative 200 newtons is equal to F minus 980. And again, when I combine like terms, and I add 980 newtons to both sides, my force this time becomes 780 newtons. And it's still positive because the force of the elevator still pushes me up. But now it's pushing with less than my weight. So now gravity is kind of doing the work and slowing me down because the elevator can't pull down against me. It can only really work in an upward direction. So I kind of circle both of these in case we need to come back and reference these later. So that's when we're going upwards in an elevator. You can see we have 2 different numbers. Now we're going to look at going down. Now, again, our accelerations we're going to kind of keep very simple and the same. This is with initial velocity equal to 0, so we're not moving. This will be with a velocity equal to 2 meters per second, and eventually we want to stop. Or I should say a velocity equal to negative 2 meters per second. Let me rewrite that so it's a little better to see. negative 2 meters per second because we're going downward again. So force diagrams do not change. We have the weight pulling us down. We have the force of the elevator, which again is our normal force pushing us up. So our equation didn't change. We have F equals ma is equal to the elevator force minus the weight. And again, we're still 100 kilograms times negative 2 meters per second squared is equal to the elevator force minus 980. And again, this is going to be negative 200 newtons is equal to Fe minus 980 newtons. Combining like terms, our elevator force is going to equal a positive 720 newtons. Now that might seem odd. We're moving down, but we have a positive normal force acting on us. But it's less than our weight. So if it's less than our weight, it can't support us anymore. So if you kind of go back to this original idea, we have 980 newtons pulling us down. Oops, sorry. But we have 720 newtons. 780. Where is this? 780 newtons. Sorry, this would be at 80. I don't know where the 20 came from. But 780 pushing us up. The net force is going to equal negative 200 newtons, pulling us downward, accelerating us in that direction. So the elevator force still pushes against us, but not with enough support to support our weight, so we start to move down. And then the last part, which is when the elevator is going to come to a stop. So again, I'm going to change colors to make that a little easier to separate. Same things, we have the weight pulling us down, we have the elevator force supporting us. We kind of work over here, F net is equal to ma. And I know that seems redundant, but it's important to kind of keep defining. I'm going to erase it just because I kind of messed it up there. Oops, messed up my eraser. I'm going to adjust this. I use my window. Okay, we'll go back to here. It's important to kind of go with the net force is equal to the mass of the acceleration. Now it's still going to equal the same elevator force minus the weight. And we kind of understand now that we're going to end up with 200 kilograms times, in this case, negative 2 meters per second squared is equal to the elevator force minus 980 newtons, the way we define positive and negative. And you can see here, we're going to end up with, sorry, this is 100. A little bit of struggle all of a sudden. This is going to be negative 200 newtons is equal to Fe minus 980. Okay. So I'm going to add these to both sides. I ended up getting, I'm sorry, there's a mistake here. My velocity is negative 2. My acceleration is a positive 2. Which makes that a positive number. Sorry, kind of a crucial mistake, but I think it's fixable at this point. That positive 2 makes this positive 200 newtons, so when I add 980 to both sides, my elevator floor force is equal to 1,180 newtons. And it's positive because it's working against the motion. So I apologize for the mistake in here. I mean, two of them though. 200 mass is really a 100 kilogram mass, and then again with the negative. But I think the idea of what happened there is very similar to the other, so it's not worth going back and correcting. Our final force here is 1,180 newtons. It's pushing harder against you than what your actual weight is to slow you down. That's why you feel heavier when you go down. And that's our idea of normal force changing in an elevator.